I should also say that the news yesterday was that this object came closest to the sun, and it received a huge amount of heat from the sun.
Mm-hmm.
And the latest report indicates that it became extremely bright, much more than expected for familiar comets. This morning, we have a report that the object got much brighter than expected, and moreover, the color of the object is blue, bluer than the sun. And that's very surprising, because usually when there is dust around an object, it should make it red.
The moment arrived. The interstellar visitor designated 3I Atlas reached its perihelion, its closest point to the sun, and performed a maneuver of cosmic precision. Across the skies, from ground-based observatories to orbiting solar monitors, every instrument capable of sight turned toward it. Humanity watched as this alien traveler carved a luminous arc through the inner solar system, revealing what happens when an object from another star plunges into our sun's domain. Ice boiled, dust escaped, energy unfolded, and in those moments, the universe whispered secrets long carried between the stars. Its journey began in the darkness between suns. 3I Atlas moved through the void on a hyperbolic path, its velocity too great for capture by any gravity well. It was not a wanderer of our system, but a visitor passing through. Long before its arrival, telescopes detected its peculiar coma, its strange geometry, and chemical traces unlike anything seen in local comets. As it drew near, the sun's radiation intensified, vaporizing its frozen crust and igniting jets of gas and dust that stretched behind it in glowing filaments. The stage was set for its dramatic passage. The date, October 29th, 2025, marked the moment of closest approach. At 1.36 astronomical units from the Sun, between the orbits of Earth and Mars, the object burned bright against the solar wind. Yet, as it approached perihelion, it defied expectations. Instead of a slow, steady brightening, its luminosity surged in violent outbursts. Solar telescopes and orbital probes captured the sudden expansion of its coma, the turbulent jets, and a striking feature, a sunward-directed plume, an anti-tail, that broke the rules of cometary behavior. This was no ordinary comet. This was an emissary from afar, revealing the unfamiliar physics of alien ice. As solar radiation grew more intense, Atlas erupted with activity. Frozen layers of carbon dioxide, carbon monoxide, and water sublimated in sequence, propelling vast plumes into space. Spectroscopic studies revealed something astonishing. The object's coma was rich in carbon dioxide, far more so than in water. The CO2 to H2O ratio was among the highest ever recorded. Such chemistry implied an origin in a region colder and more distant than the birthplace of typical comets, perhaps a realm where sunlight was a distant rumor and volatile ices were never lost to heat. As it rounded the sun, Atlas entered a crucible of light and pressure. The solar wind and radiation forced its particles into intricate streams, while the heat tore at its fragile surface. From Earth's perspective, the object disappeared behind the sun, hidden in conjunction, but our spacecraft continued to track its radiant form. Even from that blinding backdrop, its energy could not be mistaken, an interstellar ghost shimmering in solar fire. The differences between Atlas and any comet we've known grew clearer with every observation. Its jets pointed inward, its brightness rose erratically, and its composition was extraordinary. The behavior suggested formation in a volatile-rich nursery, perhaps far from its parent star, where carbon dioxide could freeze into layers that never sublimated until now. Polarimetric analysis confirmed more strangeness. The light scattering from its coma was unlike that of any solar system body, suggesting dust grains of exotic texture and composition. Telescopes across the world gathered a torrent of data: visible imaging, infrared spectroscopy, gas and dust analysis, polarization measurements, and detailed mapping of the evolving tail. This was a singular opportunity, a complete record of an interstellar visitor under the sun's full influence. Every photon carried insight. Every wavelength told part of the story. On a compositional level, Atlas redefined what a comet could be. If interstellar bodies hold chemical ratios so unlike our own, then the galaxy's inventory of matter is far richer and more diverse than we've imagined. Its high CO2 abundance suggests that some planetary systems preserve volatile ices more effectively, shaping different kinds of comets and worlds. The material Atlas carried was, in essence, a fragment of another solar system, one frozen long before our own was born. Dynamically, its hyperbolic trajectory confirmed its unbound nature. It had come from the stars, and it would return to them. Yet its behavior, its jets, its brightening, its tail, mirrored that of ordinary comets, showing that the same physical laws apply across the cosmos. Still, the deviations, the wild volatility, the reverse tail, the polarization anomalies, revealed the fingerprints of another history. It was both familiar and alien, a bridge between what we know and what we can only imagine. This event provided a rare calibration point in the study of interstellar objects. Before Atlas, we had seen only two confirmed visitors, Oumuamua and 2I Borisov. One was elusive, the other incomplete. Atlas, by contrast, arrived under perfect observation, offering a detailed portrait at Perihelion. The convergence of interstellar origin, close solar encounter, and full instrumental coverage made it one of the most scientifically significant moments in modern astronomy. It allowed us to ask, how universal is the behavior of comets across star systems? And how much of what we see is a signature of our own solar environment? The data suggested that cometary behavior, outgassing, jetting, and tail formation, is not unique to our sun's domain, but rather a cosmic phenomenon. Yet the details vary. Ratios of volatiles, surface composition, dust behavior, all shaped by each system's unique history. In this way, 3I Atlas forced us to broaden our models, to envision a spectrum of cometary physics extending beyond the solar system's boundaries. Perhaps most profound, Atlas's materials may have originated in an ancient, colder environment, a relic of a star older or dimmer than our sun. Its frozen chemistry may preserve conditions from a forgotten chapter of galactic evolution. Through its emissions, we catch a glimpse of the molecular building blocks that once orbited another star. Studying those materials through their spectral fingerprints is like opening a time capsule from another epoch. Its approach also tested the limits of small body survival. Interstellar comets like Atlas are pristine, never scorched by repeated orbits. When exposed to solar heat for the first time, their outer shells rupture violently, releasing buried ices and dust from deep layers. The intensity of Atlas's eruption forced us to reconsider how sublimation and jet mechanics operate under these alien conditions. Its rapid brightening suggested that interstellar bodies may conceal vast stores of volatiles, dormant until a star's light awakens them. The global response to Atlas's perihelion was extraordinary. Observatories on every continent, space-based telescopes in every orbit, all synchronized to capture a fleeting visitor from beyond. The collaboration between disciplines, solar physics, astrochemistry, planetary science, demonstrated humanity's growing readiness for the next interstellar encounter. The success of this observation means that when the next traveler appears, we will be prepared. The models refined through Atlas's data will shape how we detect, track, and understand the messengers that drift between stars. From a planetary science perspective, Atlas deepens our curiosity about the galaxy's unseen inventory of small bodies. If its chemistry is typical, then countless similar travelers may roam interstellar space, some rich in carbon dioxide, some in methane or ammonia, each carrying unique fingerprints of their parent stars. Such bodies may one day collide with young worlds, delivering the molecules that enable life. The materials locked in these frozen travelers may play roles in the chemistry of planets across the galaxy. In that sense, Atlas is not just a comet. It is a messenger of possibility. The geometry of its passage was fortuitous. At a distance of $1.36, The sun's heat was fierce, but not fatal. Atlas did not disintegrate entirely. It endured long enough for continuous observation from approach to retreat. This continuity gave scientists an unbroken cinematic sequence, an unfolding drama of heat, chemistry, and cosmic physics. For once, we didn't just glimpse an interstellar visitor. We watched its entire transformation play out in real time. The peculiar sunward jet remains one of its greatest mysteries. Under ordinary physics, comet tails stream away from the sun, pushed by radiation pressure. But Atlas's anti-tail appeared to defy that rule. It may have resulted from a geometric alignment, dust grains following orbital paths that projected forward from our viewpoint, or from physical processes unlike any we've modeled. In either case, it exposed gaps in our understanding of dust dynamics and radiation interaction. Scientists now revisit tail formation models, recalibrating them in light of what Atlas revealed. As it departed the sun's realm, fading back into the void, Atlas left behind a legacy of data and a profound reminder. The solar system is not isolated. It is porous, open to the drifting remnants of other stars. Each visitor carries with it the history of its birthplace, the chemistry, the heat, the dust, the light. When such an object meets our sun, the event becomes an experiment written across the sky. The star as furnace, the object as specimen, the universe as laboratory. The philosophical weight of this encounter is immense. What if most planetary systems are built from materials unlike ours? What if life elsewhere began with different molecular seeds, carried by comets whose chemistry we have only begun to glimpse? Atlas challenges us to think cosmically, to see our system as one among billions, each with its own inventory of elements, ices, and stories. The data gathered during this passage will shape comet science for decades. The brightness curve, the coma's expansion, the tail structure, the scattering of polarized light, all serve as benchmarks for models of interstellar bodies. Some findings hint that Atlas's surface materials resemble those of distant trans-Neptunian objects, formed under ultra-cold conditions where sunlight never penetrates. That possibility connects the distant edges of our solar system to the alien nurseries of others, bridging the local and the cosmic. Atlas also served as a quiet triumph of planetary defense. Though it posed no threat to Earth, tracking it across Perihelion proved the precision and readiness of our detection systems. We watched a fragment of another world race past our sun, and we followed it in real time. That ability to detect and study such visitors, no matter how brief their stay, marks a milestone in our reach as a species. Yet beyond the data and the models, the event's true meaning was emotional. To witness an object born around another star, now illuminated by our sun, is to experience the universe as both vast and intimate. In that moment, the boundaries between systems dissolve. The cold messenger from afar becomes a mirror, reflecting our own origins. The perihelion of 3I Atlas was not just an astronomical event. It was a moment of cosmic connection, where the familiar and the alien converged under the light of a single star. Each measurement, each spectrum, each fleeting photon captured a story billions of years in the making. Questions remain. Why such high CO2 abundance? How did it survive the journey through interstellar space? What secrets lie within its nucleus? The answers, like the comet itself, continue outward, beyond our reach, but never beyond our wonder.